Start recording. Okay. The last question, question 13. A scientist is attempting to model the number of insects present in a colony at time t weeks. At the start, there are 400, and after 1 week, there are 440. The scientist assumes that the rate of increase is inversely proportional to the number of insects present at time t. Okay? Write down a differential equation to model this. So let's be really careful, because this, actually, we know how these questions work a little bit. And this first thing may only be 1 mark, but it's going to be the key to the whole question. Because if we don't get the differential equation right at the start, then we're not going to be able to solve the differential equation to find n in terms of t. So this is really important that we read this carefully. The rate of increase of insects with respect to time. So this is dn by dt that we're dealing with, the number of insects with respect to time, is inversely proportional. So that means we're looking at 1 over, or k over, and it's inversely proportional to the number of insects. Okay? And that's n. So it is k times 1 over n, or some other constant times 1 over n. And it's the rate of increase. So we want it to be positive. There we are. And that's it. That's 1 mark. But that was crucial. And it's really important that we had n in there, and quite a few of you put t in there as the variable. It's not proportional to the time. It's proportional to the number of insects at the time. So part B, solve the equation. That was 1a. B, okay, well, we need to separate the variables and integrate. We need to get anything involving n on the side with dn by dt. Anything not involving n, we're going to leave on the other side. We know that we now need to integrate this. So let's do this properly. Let's put the integral sign in there. dn, and this is the integral of k dt. Let's just be a little clear about what we've done. So what we've done there, there's no great mystery. We have done the same thing to both sides of the equation. We have integrated both sides of the equation with respect to t. Okay, just to be clear that we're doing the same thing to both sides. It's not some kind of magic process. Okay, if we integrate n, we get a half n squared. Add 1 to the power, divide by the new power. If we integrate k, we get kt, and we need to put plus c in there as well, because we need to have the constant of integration. The question said, it gave us a couple of conditions. It said that if t is 0, there were 400 insects. So that means that a half 400 squared is 0k. Okay. Right. So we're going to do a half of 400 squared, and just to be certain, I'm going to do it on the calculator, because a few of you made a mistake with that calculation. 80,000 is the value of c. Brilliant. If t equals, what was the other one? 1, n is 440. So a half 440 squared is 1k plus 80,000. That gives me, I think, that k, a half of 440 squared minus 80,000 is 16800. So half of n squared is 16800t plus 80,000. What did the question want? solve this equation to find n in terms of t. So we have to end by saying what n is in terms of t. Let's double everything. What's that going to be? 3, 3, 6, 0, 0, t plus 1, 6, 0. And square root it. That, I think. Yes. There we go. Don't forget plus c at the end of your integral. You've got to have that in there, haven't you? And the clue was that they gave us 2 initial conditions, so that there must have been 2 unknowns for us to find as we worked our way through that bit. There we go. That was 5 marks for getting that far. Then we get a revised model. In a revised model, it's assumed that dn by dt is this new expression. Solve this differential equation to find n in terms of t. So dn by dt now, in part 2, is n squared over 3988 e to the 0.2t. It's another differential equation, so we're going to separate the variables and integrate. Again, just the same way. We need everything involving n on the left, 1 over n squared dn by dt. We need anything not involving n on the right, so that is 1 over 3988, well, e to the minus 0.2t. Is it all right to write it like that? Because I want it on the top line anyway for when I'm going to integrate it. I could have taken the 3988 to the other side, really, couldn't I? So that, integrate it, 1 over n squared, well, that's n to the minus 2 dn is the integral of 1 over 3988 e to the minus 0.2 t dt. Don't fall into that really easy trap that says that as soon as you see a fraction that you're integrating, or 1 over anything that you integrate it, you end up doing it as a natural log. So it's only if it's 1 over x. 1 over x squared doesn't integrate to a natural log. So n to the minus 2, add 1 to the power, divide by the new power. On the right, we're integrating e to the minus 0.2. So we divide by, let's write this out in clear stages here. So this is 1 over minus 0.2 e to the minus 0.2 t plus c. That looks a little bit messy, but that's what we'd have with this. Again, we want to find n in terms of t. So what have we got? We've got minus 1 over n. What can I do with that fraction? 1 over 3988 times 1 over 0.2. So my calculator is going to write it like that, so I may as well write it like that. It's minus 5 over 3988 e to the minus 0.2t plus c. This time, we've got the same initial conditions to work with. We know that if, what have we got to go on with this one? If t equals 0, n equals 400. So minus 1 over 400 is minus 5 over 3988 plus c, because that's e to the 0, so that's times 1 on that side. What's that going to be? Minus 1 over 400 plus 5 over 3988 gives me c as being 497 over 398800. There we are. Not particularly encouraging numbers going on here. But we've got minus 1 over n is minus 5, 3988 e to the 0.2t. Let's put that down there. Minus 497 over 398800.
That's the worst equation.
It's pretty horrible, isn't it? We're not done because we have to write n equals. But actually, they're going to be reasonably generous in this. So let's multiply everything by minus 1. And
Multiply by n and divide by all this.
well, you know, I think they're going to give us a mark for this. They're going to give us the final answer for writing 3. It's going to be horrible, isn't it? If we did 1 over that lot, then we get it. We can simplify this. It's not too bad to simplify it, because if we were sensible enough to think, actually, we could make that over a common denominator quite easily. So if we wrote it as being 500 e to the minus 0.2t over 398800 plus 497 over 398800, we've got it over a common denominator. So n is 398800 over 500 e to the minus 0.2t plus 497. And it's not pretty, but that's the answer.
Do you see how someone in the exam haven't gotten my answer wrong?
I can see how, yeah,
They got it wrong.
yeah. But you would have to know that you'd done everything right and be confident in that. Yeah, so there you are. Right, there's one final part of the question. Compare the long-term behaviour of the two models. To be fair, quite a few of you had not really got two models to compare at this stage. If we're going to compare the long-term behaviour of the two models, then what could we say? Well, the first model, as t increases, that keeps increasing, doesn't it? It would just continue to increase. It won't always. The rate at which it increases will slow down, because it's a. I'm drawing in the air, aren't I? It's a square root of x kind of graph, isn't it? We know that square root of x graph keeps on going up, but it does this kind of shape, doesn't it? It goes like that kind of thing. So the first one is something like that. So model 1 will continue to increase.
Wait, hang on, we've got cake.
We are recording, Danny.
Yeah, precisely.
Model 1 will continue to increase in population. So that describes the long-term behaviour of that one. Model 2, it's maybe a little bit more difficult to think about what's going on there.
Caps out, doesn't it?
But it does, yeah. If we think about what e to the t does, or e to the minus t, as t gets larger, e to the minus t approaches 0. That's an e to the minus x graph. So e to the minus t gets closer and closer to 0. That's root x that I've just drawn as just an illustration of thinking about what's going on with this. So if that function in there is getting closer to 0, as we get closer to infinity time, as time goes on, that's getting closer to 0, we're left with 398800 over 497. which is 802. So the population will approach a limit somewhere in the region of 802. Model 2 will approach a limit of 802.4, I think we got, didn't we? So it would tend towards a limit in the long term. There we go, and that is that. That's maths, I'm supposed to say at that point.